Hello, RenaissanceWoman here, and welcome to the third part of my 11-part video series on multivariate statistical analysis. Last time we discussed about MANOVA, where we compared joint means of multiple variable outcomes between a group variable with more than two groups. Today we are going to discuss something that's a slight modification of the MANOVA called the MANCOVA. So for this video, we will first look at the definition of ANCOVA and MANCOVA. Just like ANOVA and MANOVA, MANCOVA is the multivariate equivalent of the ANCOVA. Then I will explain the idea of the MANCOVA and how it works. Of course, just like MANOVA and other statistical tests, MANCOVA also has its set of assumptions that we must meet before we can perform the MANCOVA accurately. And finally, we get to the R demonstration part of this third part of the video series. So what is ANCOVA? First of all, ANCOVA, like ANOVA, where ANOVA stands for Analysis of Variance, ANCOVA stands for Analysis of Covariance. ANCOVA is similar to ANOVA in the sense that it compares the means of the outcome variables to see if they are statistically different from each other when we have group variable with more than two categories. But it's different from ANOVA in the sense that ANOVA only considers the influence of one variable on the outcome variable. ANCOVA is used when we suspect that the variance of the dependent variable is not explained by the group variable alone, and there are other variables that can influence the null hypothesis test by influencing the group variable's relationship with the outcome variable. So we use ANCOVA by looking at if there is a significant difference of the means for the outcome variable amongst the different groups that were given by the group variable when the covariate, when the influence of the covariate has been controlled. So MANCOVA, it's the multivariate extension of the ANCOVA, where for the outcome means we are dealing with mean vectors because there is more than one outcome variable. So now I am going to give you two examples of how ANCOVA and MANCOVA can benefit research. Now, ANCOVA and MANCOVA, they are beneficial to research because we can use them to control the influence of covariates in a study that we don't really care about. But at the same time, these covariates can influence the result of the study by influencing the outcome variable. And by using ANCOVA and MANCOVA, we are able to see the influence of the group variable on the outcome variables more cleanly because we can use ANCOVA or MANCOVA to control the covariates. Firstly, ANCOVA can correct something called the systematic bias. A systematic bias happens when we have a situation where the members in each group were not selected randomly. So when I say that the members in each group are not selected randomly, what I mean is we have a population and we are trying to draw a sample, but the individuals in the population they don't have equal chances of being drawn into this sample. This is when the selection is not random. So for example, let's say that we have a situation where we are trying to look at the mean weight lost by different races of people when they were under the same diet plan. But at the same time, we suspect that people belonging to these three races, they also belong to different age groups. And the age is a variable that could influence the amount of weight, the amount of weight loss. Because there are times that young people can lose weight much easier than people who are older. And we have a situation where there are more older people in the Asian group compared to the Caucasian group. So when this happens, since age influences the outcome variable, so it could be possible that the difference that's caused by the grouping can also be influenced by the age. So in this case, we need to control the age variable, which is why in this case, the age is the covariate, the race is the independent, the group variable, and the weight loss, the amount of weight that's lost by the people, it's the dependent variable. So in this situation, we need to control the age variable so that we can see the effect of the race variable more cleanly on how it could affect the amount of weight that's lost. So we can use ANCOVA in order to do that. And secondly, ANCOVA can also control variance of the dependent variable that were contributed not from something that's like a categorical variable. It could be a variable that's very, very continuous, and it's different for each of the individuals that's in the study data. So for example, we have a situation where we are trying to compare the driver's test grades of people from different age ranges. Now, when it comes to driver's license tests, it's very realistic that people could fail on the first attempt, and they have to retake it, and they end up passing on the second attempt. But the retake grade, the grade of the second attempt, could very much be influenced by the grade of the first attempt, because the first attempt could show the driver where they need to improve. And let's say that we have a situation where we have the variable for the people who did their first attempt but failed. This is our covariate. And we have a variable that's categorical, which is people of different age range. And we also have the outcome variable, which is people's test grade for their second attempt where they passed their driver's test. And we're trying to see people of whether or not there is a difference between people belonging to different age range and the grade that receive on their past test. But in this case, let's say that in different age ranges, let's say if we have older people who received a very low grade for their first attempt, for people who are older, this could very much influence the outcome variable through the age range variable. So because of that, in order to see the influence of the age ranges variable more clearly, this group variable, we need to control for this covariate, which is the grade of the first attempt. So again, we could use ANCOVA to control this covariate right here so that we can see more cleanly age ranges influence on the grade of the second attempt of the driver's test. Now, for the two examples that I've just discussed, I only consider situations where there is only one outcome variable. So in these cases, ANCOVA should be used in order to control for the covariate so that we can see cleanly the effect of the group variable on the outcome variable. But for MANCOVA, we can use the same situations. It's just that we need more than one dependent variable in order to use MANCOVA. So the situations are, they can be the same. It's just that the outcome variable, we need to be looking at more than just one outcome variable. And the covariate, it's the same. So now that we learned what types of scenarios we should apply ANCOVA, you might ask me, how does ANCOVA actually work mechanically? Now, ANCOVA is actually a hybrid of the ANOVA and the regression methods. So it's a hybrid. And ANCOVA uses the regression method in order to calculate a new adjusted mean for each group using the covariate. When we use this method to control the covariate, and the adjusted means are then reanalyzed to see if they are truly different from each other between each different groups that were given by the group variable. So to look at ANCOVA mathematically, it can be represented by this equation right here. This represents the so this variable right here, this mean, I should say, it's the adjusted dependent variable mean for group J, and there can be as many number of groups as the group variable states. This one is the dependent variable mean in group J before the adjustment. Let's say if we were doing an ANOVA, then this would have been the original mean. That means between the groups that would be analyzed for the ANOVA. And because that in this case we have a covariate, we have to modify it so that we get an adjusted mean for that. This B is the common regression coefficient, which represents the way the covariate could influence the outcome variable for group J. And this right here is the mean of the covariate variable for group J, and this is the covariate mean for the entire sample. Now, as you can see that this equation, it only calculates the adjusted dependent variable mean for group J. This means that we need an equation like this to calculate the adjusted mean for every single group. So as many number of groups there are, the number of this equation that we must consider. Also, the null hypothesis for an ANCOVA would look something like this. So we have the adjusted dependent variable means between each group. So we compare them and see how different they are amongst each other. And the null hypothesis is that they are not different from each other. Now that we understand the arrangement of the ANCOVA, the arrange of the MANCOVA, it should be quite intuitive for you. So it is similar to the ANCOVA, except the adjusted dependent group mean is a vector of multiple means because we have multiple outcome variables. So for each group, we have a mean for variable 1, variable 2, and variable 3. In this case, I considered a situation where we have 3 outcome variables. So what we do is for the null hypothesis that we're testing, we assume that the adjusted mean vectors for each group, they are the same. There's nothing different between them. So this is the mean vector for all 3 outcome variables. For group 1, C, the J, they all equal to 1 here, and this is for group 2, and this is for group J, and there's J number of groups in this case. So like all statistical tests, there are assumptions that must be met before any test performance can begin accurately. So for ANCOVA, the dataset must satisfy the assumptions of the ANOVA as well. And these assumptions, I have already discussed them in the MANOVA video. So if you want to hear me elaborate on these again, feel free to go watch that video. But for ANCOVA, there are also additional assumptions that we must meet in order to perform it. So the first assumption that we need to prove is that the dependent variables for a MANCOVA, this is actually for a MANCOVA because it says dependent variables. For ANCOVA, there would only be one dependent variable. These variables must be continuous, and the group variable must be membership exclusive, so one person cannot belong to more than one group. And there must be a linear relationship between the dependent variable and the independent variables, the group variable. Also, the covariate, it should be related to the dependent variable, but it shouldn't be related to the group variable. And these two are very important assumptions. Now, for the R demonstration part of this video, I will only show how to test for these 2 assumptions because these 3 assumptions are quite intuitive. You can just do them by yourself if you have an elementary amount of experience in statistical analysis. But if you don't have the experience to do these, please leave me a comment in the comment section and I can do a demonstration for this one as well. Now, the 7th assumption, let's get back to this. The 7th assumption that we need to prove in order to perform an ANCOVA is that the regression lines for different groups should be parallel. And when I say regression lines, it's the regression that we use to calculate the adjusted means that I just showed previously. So the way we check for this assumption is we introduce an interaction term of the group variable and the covariate to see if this variable is significant. And if this variable is significant, then the regression lines between the groups cannot be parallel. And the last assumption that we must meet is the homoscedasticity of the regression slopes, and this we can check by comparing the mean square errors of the separate group regressions. So let's say if we have J number of groups, there will be J number of regressions, and homoscedasticity, it just means that if we have a line and there are dots of the outcome variable around this regression slope. These dots, they must have relatively equal distance between themselves and the lines. Okay? Okay, so finally we get to our demonstration part of this video. So the data set that I'm going to use for this demonstration, it's a data set that was published in a book called Applied Multivariate Statistics for the Social Sciences, and it was written by Stevens, published in 2009. You can take a look at that book if you are interested in multivariate analysis more deeply than just this video. So this data set, it has 29 individuals. It has a group variable, and in my demonstration, I call this variable group ID. And this group variable, there are two categories. We have male and female. And the outcome variables, this is a MANCOVA demonstration, so we have more than one outcome variable. So these two are the two dependents, and they are actually the scores on two tests that were taken by these 29 individuals. And we have one covariate, and it's just written as covariate in the demonstration that I'm going to do. So these are just the variable names that I've used for my own demonstration, okay? And this variable is the score of a previous test that was given before these two tests. So what they're trying to do is they're trying to compare the scores of these two tests among the males and females in this sample. But there is a covariate that could influence the scores of these two tests, which is a pretest that was given between these two tests. So in this situation, what we want is to control this covariate, the previous test score, so that we can see cleanly how the gender of these 29 individuals influences the scores of these two tests. Okay, so now we're going to write and run some codes to perform this MANCOVA that I've just described. And first of all, and this is something we should always do before we perform an analysis, is to install the proper R packages that we need for this analysis. And in this case, I need the packages car, psych, and effects. So I'm just gonna run these codes. And this might take a little while. Okay, so now we can use the library function so that we can access the functions that are in these packages. Okay, so now what we can do is we can enter the data numbers into a matrix. Now the data sets, when we are using them in the R space, what we're actually using is a matrix of all the values that are in this data set. And this data set, the way that I'm going to enter it, it's going to be like this. And so first I'm going to enter all the data for people who are in group 1, so people who are males. Okay? So all I need to do is run this whole thing, or I can put this in the beginning also and run it. So if I want to run it, it's just Control Enter, quite easy. And this function right here is called the matrix function. So what the matrix function does is it can make whatever numbers that you put into this in a vector. This C, it shows that all these numbers are in a vector. So the bracket starts here and end here. And what this matrix function does is it tells the R that it wants to make a 15-row matrix with 4 columns. Okay, so what we're gonna get from this is a matrix that's 15 rows and 4 columns, and these numbers are the numbers here. Okay, and for group 2 it's the same thing. It's just that in this case we have 14 rows and 4 columns. So we run this and we can see the outcome of the matrix for group 2 as well. Now, we need to combine these 2 matrices into a single data set. So what we can do for here is we use the data frame function to do that, and inside this data frame we use the rbind, the row bind function to combine group 1 and group 2 by combining them by rows. So in this case, group 1 will be on the top and group 2 will be at the bottom. So now let's look at this data set itself. So this data set, I named it MANCOVA data set right here. This arrow, it just names this joint data frame to this name right here. So all I have to do is type the name and then run this line, and it gives me a 15 plus 14 is 29, so 29 rows. So 4 columns, and from 1 to 15 it's for males, so this categorical variable is 1, and the rest are 2s, they're females. So as you can see that from this matrix, what we don't have here is the name of the columns, the name of the 4 variables that are involved in this analysis. So what I can do is I can name the columns of this matrix by using the names function. So put names and put the name of the matrix into this function, and then I assign it this vector of these are strings. These are the names of the names of the of each column of each variable. So we have the group ID, we have the covariate, we have the 2 dependents, right? So all we have to do is run this line, and so now we have, now if I were to run this one again, the name of this matrix, I'm just going to rewrite this here so that things are more clean. So I'm gonna run this, and you can see that now the columns have names. Awesome. Everything's good. Great. So we're gonna keep on moving, and these 2 lines I probably don't need them, so I'm just gonna comment them out. If you put a hashtag in front of the line, it should cancel out the entire line of code. So next I'm going to attach this data set, the MANCOVA data set, where the data set that we're going to perform ANCOVA on. MANCOVA, sorry about that. So we use attach so that we can use the variable names to specify for each variable. And next we're going to test the 2 assumptions that I was explaining in the theory part of this video. So first we need to test the assumption that the regression line for the groups are parallel, and we do this by first introducing an interaction term of the group variable and the covariate. So what we do here is first we create a joint variable of the two outcome variables by using the two dependent variables that are inside of this matrix. So when we write the matrix name and we put a $ here, and then afterwards we put the variable name, it means that I'm referring to the variable that's inside of this matrix, this data set. And we're using cbind, so we're using column bind, so that these two variables should be beside each other by columns. So if we look at this outcome right here, it should give us a two column matrix with the values of the first dependent variable and the second dependent variable. So now what we do is we use the MANCOVA function, and because this is a one way MANOVA. Let's say if we didn't have this covariate in the picture, this would have been a one-way MANOVA because we only have one group variable, right? So what we do is we just use the regular MANOVA function that was built inside the R system to do this. So this is relatively easy. So if you didn't watch the MANOVA video, we have the outcome variable here, and we have the group variable here, we have the covariate variable here, and there's a plus sign between them, and we have the interaction term of these two variables here. And the data set, of course, is the MANCOVA data set. So what we do is we run this MANOVA. Okay, that's done. And we try to calculate these statistics, if you remember. And this is going to be a type 3. Okay, so just by running the first one, I can already see that the interaction term is not a significant one. So in this case, this assumption passes the test because we want the regression line for the groups to be parallel, right? So if there is an interaction term, if the interaction term is significant, then this assumption doesn't pass. But if it's the other way around, that the interaction term is not significant, then this assumption is valid. It passes the test. And if I were to run the to find the other statistics for the MANOVA, they should give me just about the same result. So this one is for Roy. See, the interaction is not significant. This one is for the Hotling, and this one is also not significant. And this one is the Pili, which is also not significant. So assumption 7 passes the test. Now, before we do the MANCOVA, or if we carry on with the other assumption tests, I like to first look at the means of the outcome variables between the two groups before I carry on with the test. So I use the describe by function, and this function is contained in the psych package. So we enter the data set, and we enter the group variable right here. So if we run this, we should be able to see a lot of different statistics for group 1 and group 2, and one of them is the mean for the outcome variables. So for group 1, we can see that the first dependent variable, the mean is around 12.2, right? And for the second dependent variable, the mean is around is 5 in group 1. So for group 2, the mean of the first dependent variable is 13.79, and the second one is 10.50. So what we are trying to see is whether or not the means of the first group, which are these numbers right here, this vector, whether or not this vector is significantly different from this vector. And the null here is that they are not significantly different. So now we can start calculating the adjusted means for the different groups. So these means, they are not adjusted yet. So to calculate the adjusted mean by controlling the covariate, what we need to do is use the analysis of variance function, and this function is just built inside of the R program, so we can readily use it. But first, we have to state that the group ID is the factor, is the group variable. So we run this line in order to do that. And first, for group 1, we need to calculate the adjusted means. So first, what we do is we run this ANCOVA function, and this ANCOVA function, since it's for group 1, we only have the first dependent variable here, and we have the covariate and the group ID for this, because we need this to calculate the adjusted mean. So first we run this ANCOVA, and then if we were to look at the information that we get from this ANCOVA, using the summary function, we put the name of this ANCOVA in here, and we're trying to look at the type 3 for this. So as you can see, this is the MSE, the mean square error, for the covariate and the group ID. And as you can see that for group 1, these two variables, they are all significant when it comes to influencing the outcome variable. So this is all that this ANCOVA explains. Okay, so now this line right here, this effect function is used to actually calculate the adjusted mean for group 1. So we have the group variable, we have the ANCOVA model, and this function, we are telling it to give us the standard error as well. So we run this, and we look at, we use the summary so that we can actually see the adjusted means. And as you can see, for the two variables, the two outcome variables, this is the adjusted mean for group 1, and this is the adjusted mean for group 2. So let's write this somewhere so that we can remember it. I'm going to put a hashtag there because this is not really a code, this is just notes for us. So we have 12.00555, and the second one is 13.99406, right? So this is the first adjusted mean. And for calculating the adjusted mean for the second group, it's pretty much the same thing. So first, what we do is we build an ANCOVA model with the second dependent as the dependent right here, and also the covariate and the group ID, and also using this data set. So we run this line and we use the summary function so that we can see the information right here. And this information right here shows that the covariate is actually insignificant for the second group in terms of influencing the outcome variable. Now, I'm going to stop here for a second because I want to address this assumption as well. So what I did here actually is that I could test for this assumption. So you saw how I built a different ANCOVA model for the previous group. This is for group 2. I did the same thing for group 1. So if we were to compare the mean square values of these two variables, so we have here 17.66 and 211.59 here, right? Now, if we were to look at the information for the previous one, sorry about that. So if we were to rerun this, we can see that this is the mean square value for the first group, and both of these variables are significant here, right? This is for the first group, but for the second group, what we have is something different. You can see that this is the information for the second group, and the mean square values are really different, right? And also the p-values, they're different. This covariate is significant, this covariate is not significant. So in this case, this assumption is actually violated. Okay, so in this case, using this data set, we can't accurately carry out a MANCOVA for this data set because it failed this assumption right here. Now, the reason that I chose this example is because in research, sometimes these assumptions do fail for certain data sets, but a lot of researchers would choose to use this method anyways because it's the best method they have for their research. So sometimes MANCOVA is used even though the assumptions are not all met. But let's say if you were one of those researchers who have a situation that you have to use MANCOVA even though it violates some of these assumptions, what you need to do is you can take the adjusted means. Now I am going to calculate the adjusted means for the second group as well so that you can see. So what I do is run this line right here, and we look at the adjusted means, and the adjusted means here are these numbers right here. So 5.0 something. Put a hashtag there, and we have a comma, and we put this here. Put it like this, and you can see that these are the means. These are the mean vectors, right? What you need to do is just compare these differences, just like a Hotelling t-square test or a MANOVA test. But in this case, since we only have two groups, you can use the Hotelling t-square test to compare these. But even though I wouldn't recommend it because it does violate one of the assumptions, but sometimes in research we don't have a lot of choice. Now, I kind of showed you guys a long way of doing MANCOVA itself, but there are better ways to do this. There are other packages where we can install so that we can use a function which is called MANCOVA, so it can do everything for us in just a few lines, much less coding than this. But the reason that I don't have this in my video here is because the version of my R program, my R Studio, it's not the version where this package can be installed. Now, I am more than happy to show you how to use this package and how to use the function in it. It's called MANCOVA, so that we can use it to very cleanly analyze a data set that needs MANCOVA. Now, if you want to see this, please specify in the comment section so that I can do a separate video for you. And I can also make a separate video where I can show you how to install RStudio, which is the IDE, and the R itself, other versions of R, so that you can choose the packages that is suitable for your environment. Okay, so that's my MANCOVA video. So if you have any questions, please feel free to leave me a comment in the comment section. And if you like my video, please feel free to subscribe or like the video. And I also have a Facebook fan page. You can like my Facebook fan page if my videos are very useful to you. So once again, thank you very much for your attention, and remember, life is short. Try everything and be everything. Thank you.